Hello students, I am Dr. Manisha Verma, teaching physics to undergraduate students in the University of Delhi. Lately, in my last lecture series, I have started telling you briefly about various topics in thermal physics. I dealt with heat engines in detail in my last lecture and also started with a discourse on real gases. To understand real gases, I have to tell you briefly about various experiments that led us to the concept of the understanding of real gases. Just to recapitulate briefly, let me tell you, real gases do not obey gas laws. That is, they show a marked deviation from ideal gas behavior. A gas which follows the gas laws exactly is known as an ideal gas, and one which does not is called a real gas. At high temperatures, real gases behave like ideal gases. Let me again remind you students that it is not that hydrogen is a real gas and oxygen is an ideal gas. All the gases can be real and all the gases can show ideal gas behavior depending upon the temperature and pressure of study. To understand the behavior of real gases, scientists performed various experiments which showed that real gases exhibit non-ideal behavior or nature. That is, they show a deviation from the ideal gas behavior. Amongst these scientists, Regnault, Andrew, Amagat, and various other scientists are very important to study. Just to briefly tell you what is expected, let me tell you, ideal gas follows gas laws, that is Boyle's law and Charles' law. The molecules which comprise an ideal gas, the forces between the molecules which comprise the ideal gas is zero. The size of the molecules of the ideal gas is negligible, and the ideal gas follows the kinetic theory of gases accurately. Now, what is Boyle's law? According to Boyle's law, the product of pressure, P, and the volume is constant at a constant temperature. Therefore, for ideal gas, due to change of pressure, PV should be constant at a constant temperature. That is, V is inversely proportional to pressure. This means that if we plot PV with respect to P for an ideal gas, we should get a horizontal line which is parallel to the x-axis. Now let me tell you what is the Regnault's experiment. As you can see from the graph that is being shown on your screens, we have plotted PV versus pressure. The variation of pressure is from 200 to 1000. Now, ideal gas behavior is such that we obtain a horizontal line which is parallel to the x-axis. But as we see from the graph, nitrogen, oxygen, hydrogen, helium and carbon dioxide are showing a markedly different behavior from the ideal gas. Carbon dioxide shows a decrease in PV. It reaches a minimum and then starts increasing. Now let me briefly tell you about the behavior of these gases at different pressure in detail. For a fixed quantity of an ideal gas at a constant temperature, PV should remain a constant in spite of the variation of P. This is what is expected of an ideal gas. Consequently, the plot of PV against P should be a straight line parallel to the x-axis. That is, PV should not vary with pressure. In the case of gases containing small molecules like hydrogen and helium, the value of PV increases steadily with the increase of pressure from the very beginning. So this is very much different from ideal gas behavior. But for oxygen, nitrogen, carbon dioxide and other gases containing big molecules, PV first decreases, reaches a minimum and then rises with increase in pressure. So again, these gases are showing a behavior which is markedly different from the ideal gas. Ideal gas, we should get a horizontal line parallel to the x-axis, But for these gases, the behavior is very much different. Some gases are showing increase with pressure, but other gases are showing a decrease, reaching a minimum, and then showing an increase with pressure. So this is Regnolds experiment. Now next experiment that I would like to discuss is the Amagat's experiment. A very, very important experiment, because Amagat's experiment led to the concept of Boyle's temperature. Let me briefly recapitulate what I told you in my last lecture series about Andrews experiment. The Andrews experiment led to the concept of critical temperature, TC, which showed that below a certain temperature gases can be liquefied, and above that temperature no gas can be liquefied even though you apply a very, very high pressure. And remember, ideal gas cannot be liquefied at any temperature and any pressure. The very fact that certain gases are being liquefied shows that real gases are different from ideal gases. Now coming back to Amagat's experiment. Amagat determined the volume of different real gases at different pressure as high as 3000 atmosphere and at different temperatures. He also plotted PV against pressure in a graph where he got several lines. These lines are called the Amagat's curves. It is seen that the curvature of the isotherms decreases as the temperature increases. For temperatures less than the critical temperature, isotherms have a straight line portion which is parallel to the PV axis. For these temperatures, that is, for temperatures less than the critical temperature, volume decreases even though pressure remains a constant. This corresponds to the condensation of the gas. At temperature equal to the critical temperature, the straight line diminishes to a point. The minimum of the isotherm gradually switches away from the origin towards the right as the temperature increases. However, after a particular temperature, it starts shifting to the left. That is, the minimum shifts to the left of the x-axis. If we plot the locus of these minimums, it is almost a parabolic curve. And this locus of the minimum is shown by the dashed line. The parabola cuts the pressure equal to 0 axis at some high temperature. This temperature is the Boyle's temperature. For temperatures exceeding the Boyle's temperature, the value of PV increases steadily. So this curve is showing the findings of Amagat's experiment for carbon dioxide gas. Now please remember, students, Andrews' experiment was also limited to carbon dioxide gas. So here you can have a comparison between the Andrews experiment and Amagat's experiment. If you remember, in the Andrews experiment we got certain horizontal line portions in the curves. Here we are not getting any horizontal lines. In fact, we can see that for temperatures less than Tc, carbon dioxide gas is showing a vertical portion also, which is very different from Andrews' experiment. The dashed line is showing the locus of all minima points and constitutes the parabolic curve. Now let me move on to another very important aspect of real gases, which is the On's equation of state. Kamerlingh-Onnes proposed an empirical equation of the form PV is equal to A plus BP plus Cp square plus so on so forth. Now this is purely an empirical equation. It can also be written in the form of volume. PV is equal to A plus B by V plus C by V square plus so on so forth. Here the constants A, B and C are characteristics of a gas at fixed temperatures and are called the virial coefficients. Since this equation is expected to reproduce the equation for a perfect gas when P approaches 0, the first virial coefficient will be equal to RT for 1 mole of the gas, which gives us that the first virial coefficient A has to be equal to RT. The second virial coefficient varies in a similar way for all gases. It has negative values at very low temperatures. As the temperature increases, it gradually rises through 0 and becomes positive. At the room temperature, B is less than 0 for oxygen, nitrogen and carbon dioxide. It is greater than 0 for hydrogen and helium. But for all gases, B is equal to 0 at the Boyle's temperature. So B can be greater than 0, can be less than 0. To determine the Boyle's temperature, we use the following formula. At T equal to Tb, Pv is equal to A and delta Pv by delta P is equal to B. Constant C is always positive. Next, let me move on to the very famous van der Waal equation of state. In 1897, van der Waal modified perfect gas equation Pv equal to RT by applying correction factors. He applied correction factors for two particular aspects: the intermolecular forces of attraction that exists between the molecules of the real gas and the finite size of molecules. The equation he derived was P plus n square A by V square into V minus Nb equal to nRT. The correction for pressure was obtained in this manner. Van der Waal observed that the net force acting on molecules inside the vessel is 0. It means the molecules that is in the interior of the vessel does not experience any net force, because it is surrounded by all molecules and all molecules exert some force on the molecule, and therefore the net force acting on the molecule is 0. However, this is not the case for molecules which is on the surface of the vessel and at the walls. At walls and at the surface, it experiences a net force because it is pulled back by other molecules. Therefore, the velocity and momentum is less than that would be in the absence of force of attraction. This reduction in momentum results in the decrease in pressure than what would be the actual pressure. Now let us calculate how to find out the pressure correction. The number of molecules striking per unit area per unit time on walls and the resultant inward pull of cohesion on striking molecules. Each of these factors contribute pressure correction factor, and this is proportional to the density of the gas. So the corrected or the real pressure would then be P plus P, that is P plus A by V square, where P is the observed pressure. Due to the finite size of gas molecules, the actual size available for the movement of gas molecules is less than the volume of the vessel. Molecules have a sphere of influence around radius 2r within which no molecule can penetrate. Now let us calculate the volume correction factor. Volume of one molecule is represented by x and will be equal to 4 by 3 pi r cube, as is the volume of a sphere. This figure is showing a collision of two molecules. The two molecules encounter each other, then the distance between the center of the two molecules would be sigma. And as you can see, the second molecule cannot penetrate any further. The dashed line is showing the sphere of influence. The volume of sphere of influence for each molecule is equal to S and is equal to 4 by 3 pi 2r cube, and this will be equal to 8x. The volume available for first molecule is V. The volume available for the second molecule will be V minus 8x, which will be equal to V minus S. The volume available for the nth molecule will be V minus N minus 1S. To calculate the average space available for each molecule, we add up the total volumes and divide by the total number of molecules. So which will be equal to V plus V minus S plus V minus 2S plus V minus N minus 1 S divided by N. If we expand this formula, we get NV by N minus S, 1 plus 2 plus 3 plus so on so forth, N minus 1 divided by N. Expanding it further, we get V minus S by N, N into N minus 1 by 2. Expanding it further, we get V minus Ns by 2 plus S by 2. As the number of molecules are much larger than S by 2, the average space available for each molecule will be V minus Ns by 2, which will be equal to V minus N into 8x by 2, which will be equal to V minus 4 times Nx, which will be equal to V minus B. Here B is 4 times Nx, that is 4 times the actual volume of molecules. Thus we get the equation of state for a van der Waals gas. So for 1 mole of gas, the van der Waals gas equation of state is P plus A by V square into V minus B is equal to RT. A and B are van der Waals constants. Remember, the first term P plus A by V square is showing that real forces experience a reduction in pressure in comparison to ideal gases, and the second term V minus B is showing that the real gases experience a reduction in volume in comparison to the ideal gases. This is a very important equation of state and it is shown in this graph. The solid line is showing the variation of equation of state of the real gases. The upper dashed line is showing RT over V minus B variation and the lower is showing the variation of A by V square. If we combine these two equations, we get the dashed line. Now let us interpret this equation. For large V, pressure exceeds A by V square and B becomes negligible in comparison with V. The equation then reduces to the equation of state for an ideal gas. Let us now compare the equation of state for a van der Waals gas with the experimental results. The van der Waals gas can be written in this form also. P is equal to RT over V minus B minus A by V square. When expanded in powers of V, this equation takes the form PV cube minus PB plus RT V square plus A into V minus B is equal to 0. As is clear from this equation is cubic in nature because it has V cube in it. So again I repeat, we note that this equation is cubic in V. So what does this mean? This means that for each pair of values of P and T, V will have 3 values. Either all values will be real or 1 will be real and 2 imaginary. For low temperatures, 3 positive real roots exist over a large range of values of pressure. As the temperature increases, these roots approach one another and become equal at T equal to Tc. Now what is Tc? Tc is the critical temperature. Above Tc, only one real root exists for all values of P, implying that there can be no condensation in this region. Very, very important. Above the critical temperature, there can be no condensation. This holds true for real gases. For large values of V, for large values of volume, pressure would be small. And in the limit, V approaches infinity, pressure approaches 0. On the other hand, as V approaches B, B is what? The van der Waals constant. P approaches infinity. This implies that the curve will have an upwards concavity in the pressure versus volume plot. Very, very important result. V cannot be less than B. Yes, it cannot be less than B because in the equation of state we have V minus B. If V is less than B, we will get a negative sign. This will lead to negative values of pressure which is not acceptable. Pressure always has to be positive. This graph is showing the theoretical isotherms obtained for carbon dioxide. What is meant by theoretical isotherms? Theoretical means based on van der Waals equation of state. Isotherms, the curves obtained at certain fixed temperature. Now you can see these are very much different from the isotherms obtained from Andrew's experiment, because as you can see there are no horizontal portion, the horizontal portion present in Andrew's experiment is missing here. At low temperatures, of course, you can see some kind of similarity, but apart from that there is no similarity. This curve is also showing the similar thing, but in a different way. Now, as seen in the figure, the qualitative shape of the curve resembles the experimental isotherms of Andrew's experiment. This means that the qualitative shape of the curve obtained from the van der Waals equation of state for a carbon dioxide gas resembles the experimental isotherms obtained by Andrew in his experiment on CO2 gas. However, there are variations at low temperatures, as I mentioned just now. For instance, van der Waals equation predicts a maxima and minima in the straight line region of Andrew's curve. To explain this, let us consider van der Waals isotherm at 13.1 degrees Celsius. The portion AB and FK represents the gaseous and liquid states respectively. The portion BC is very special because it represents the supersaturated vapor and the portion EF represents the superheated liquid. Both of these correspond to the metastable state. It means it is not a stable state, exists only for a very short time and do not occur in the Andrews curves, which represents stable equilibrium. So this is one very big difference between the theoretical isotherms obtained through van der Waals equation of state and the experimental isotherms obtained by Andrew's experiment. The portion CDE indicates that the volume should decrease as the pressure decreases. This corresponds to a collapsible state and cannot be realized in practice. So this is again a major difference between the theoretical isotherms obtained through the van der Waals equation of state for CO2 gas and the experimental isotherms obtained from the Andrews experiment on CO2 gas. Again, we are comparing the theoretical isotherms and the experimental isotherms for both for CO2 gas only. Hence, we can note that a proper interpretation of van der Waals curves helps to resolve an apparent discrepancy with the observed results. We can also calculate the units of van der Waals constants. From the equation we have P plus AN square by V square, there is a misprint here, into V minus NB is equal to nRT. If PA is the pressure correction term, called often the internal pressure of the gas, then A is equal to PA into V square by N square. Units of PA is atmosphere, V square is liter square and N square is mole square. So just taking the mole square in the numerator, we get A is equal to atmosphere, liter square, mole minus 2. To find out the units of B, we note that NB is equal to unit of volume, say liter. So B is liter mole minus 1. So this is as far as the units of van der Waals constants are concerned. We have discussed right now the derivation of the van der Waals equation of state and the various experiments that are needed to understand the behavior of real gases. In my next lecture, I will be discussing more on real gases. Good day.